this short video, I will talk about cohomology and hypercohomology. So let's start with cohomology. Consider X a topological space, and over X consider a sequence of sheaves such that they form a short exact sequence. We want to know when this short exact sequence remains exact in global sections. It turns out that in general we have this exact sequence, but this last map is not always surjective. This motivates the definition of the cohomology groups with coefficients in a sheaf. In fact, this cohomology group will appear as abstractions to this problem of determining when this exact sequence extends to a short exact sequence. At the end, when we have defined these cohomology groups, we will always obtain a long exact sequence in cohomology, which will be as follows. So in here, the H0 groups, the 0-degree groups with coefficients over any sheaf, they will correspond to the group of global sections of the sheaf F. And so here, this long exact sequence will be an extension of our exact sequence that we have upstairs. Moreover, these cohomology groups will be functorial in the sense that for every morphism of sheaves, we will have a corresponding morphism of cohomology groups for every K. So let us now introduce an explicit definition of these cohomology groups. So consider U to be an open covering of the topological space X. Assume that this open covering is indexed by some set which is linearly ordered, and take F to be any sheaf over X. And also consider a number P greater than or equal than 0. So we define this space of P check cochains as follows. It is denoted CP of UF and corresponds exactly to the product of all sections of the sheaf F over the intersection of P+1 open sets of the covering. This will correspond to an abelian group, and over these abelian groups we can define differential morphisms. This is called the check differential and is defined as follows. So delta will be a map from CP to CP+1. So it will take a P cochain to a P+1 cochain in the following way. So recall that if F is a P cochain, then it is a function defined over every set of over every intersection of P+1 open sets. So here, this index I0 until IP+1 is denoting the indexes of the open sets that we are intersecting in CP+1. So here we have P+2 open sets. And so we define the delta of F to be the alternating sum of F defined over the intersection of P+1 of these P+2 open sets, where in each step we are removing one of these elements in this intersection. So it is an exercise to check that this map is well defined. It is a morphism of groups, and moreover, it defines a complex of abelian groups. This means that the composition of this map with the next one is always 0. Once we have this complex, we can define the check homology groups in the following form. So it will always be a group related to this open covering, and it will correspond exactly to the cohomology of the complex given by the check differential. And so by definition, it is the kernel of the map delta modulo the image of the map delta. This is not always equal to the cohomology group, but once we note that the check homology groups are ordered by the relation of refinement of open coverings, we can take the direct limit over all open coverings of this check homology group, and the resulting group is the chief cohomology group. Since we are interested in computing chief cohomology groups by using check cohomology groups, we need to understand first some preliminary concept, which is called the concept of acyclic chiefs. We define an acyclic chief as follows. So we say that a chief F over a topological space X is acyclic if all the higher cohomology groups are 0, right? So possibly the only one which can be non-zero is the global sections, the H0. Some examples of acyclic chiefs are the following. So first of all, our first example is the case of flabby chiefs. So a flabby chief is a chief where the restriction map from the global sections to any open set is surjective. In other words, this means that we can extend any section defined over any open set to the whole topological space. These chiefs are important for several constructions and proofs of some properties of chief cohomology. And the most important property is that for every chief, we can always consider this chief as a subchief of a flabby chief, which can be constructed as follows. It will be just the product of all stalks of the chief over all points of the topological space. In other words, the sections of this flabby chief will correspond to the discontinuous sections of G. Other way to construct acyclic chiefs is in the case of when we are constructing chiefs over a smooth manifold. So consider X to be a smooth manifold, let A to be the chief of infinity functions defined over X, and then every A module will be a fine chief. These chiefs are always acyclic, and this is due to the fact that in the space of infinity functions defined over X, we can always produce partitions of unity. This implies in particular that the chiefs of infinity forms over any smooth manifold are fine and so acyclic. Moreover, in the case where X is a complex manifold, the chiefs of PQ forms are also A modules, and so they are also fine, and so they are acyclic too. In the case where X is a complex variety, and moreover is a Stein complex variety, every coherent OX module is acyclic. Examples of Stein complex variety are the polydisk, the extended polydisk. This includes the affine space Cn and any class analytic subvariety of polydisk or extended polydisk. In particular, every affine algebraic variety is Stein. Examples of coherent sheaves over an analytic variety are the sheaves of analytic K-forms. In the case of an algebraic variety, of an affine algebraic variety, every quasi-coherent sheaf is acyclic. For instance, the sheaf of algebraic differential forms are always quasi-coherent. With this concept of acyclic sheaves, we can introduce some methods to compute sheaf cohomology groups in terms of check cohomology groups. So the first result tells us how to compute a sheaf cohomology group in terms of the usual cohomology of a complex. So consider F to be a sheaf, the sheaf which we want to compute its cohomology, and assume that F dot is an acyclic resolution of F. This means that every sheaf in F dot is acyclic, and moreover, once we plug F in the beginning of this complex, this becomes a long exact sequence. Then the sheaf cohomology group of F can be computed as the cohomology of the global sections of this complex F dot, which is just this definition. This is the usual definition of the cohomology of any complex, right? So an example of application of this theorem is the following. So consider X to be a smooth manifold. We know that by Poincaré lemma, the complex of C-infinity forms over X is a resolution of the constant sheaf R over X. Hence, using the previous theorem, we conclude that the sheaf cohomology with coefficients in the constant sheaf R is isomorphic to the cohomology of the global sections of the complex of differential forms, which is just by definition the usual de Rham cohomology groups of X. So this is a way to prove de Rham's theorem. So another method to compute sheaf cohomology groups is using Lerais theorem. So consider F to be any sheaf over X, and let U to be an acyclic open covering related to F. This means that whenever you take any intersection of open sets inside this open covering and you compute the higher cohomology of F, they are always vanishing. Under these conditions, we can compute the sheaf cohomology of F in terms of the usual check cohomology with respect to this open covering. In particular, an application of this theorem is that in the case where we're working with an algebraic variety, we know that every affine open covering is acyclic related to any quasi-coherent sheaf. And so we can compute the sheaf cohomology over an algebraic variety of any quasi-coherent sheaf in terms of an open covering, which is an affine open covering, and using the check cohomology definition. Okay, so let's now introduce the second concept of this video, which is the concept of hypercohomology. So consider now F dot to be a complex of sheaves over a topological space. As in the case of the sheaf cohomology, now we want to introduce an abelian group associated to any complex of sheaves. So for this, we need first to have the existence of an open covering U, which is acyclic related to all sheaves appearing in the complex. So let us assume that this exists, and then we can consider the double complex C dot U F dot, where one differential is the usual differential of the complex F dot, and the other differential is induced by the check differential delta. So the induced simple complex L dot D is defined as follows. So Lk will be the direct sum of the groups of check cochains C, J, U, F, I, where I plus J is equal to K, and the differential of this complex will be given by the sum of the two differentials of the double complex. So with this definition, we will obtain a complex L dot, and the hypercohomology group will be defined as the cohomology groups of this complex. In particular, the elements of the hypercohomology group, they are always represented as follows. So there will be an element omega, which will be written as a sum of terms omega i's, where each omega I will be a check cochain. And moreover, this collection of cochains, they will satisfy this kind of relation. Okay, so some of the first properties that this hypercohomology group have are the following. So first of all, these hypercohomology groups are also functorial. This means that for every morphism of complexes of sheaves, we have an induced morphism of hypercohomology groups. And moreover, they also satisfy that for every short exact sequence of complexes of sheaves, we have an induced long exact sequence in hypercohomology. So finally, I want to give some properties regarding to isomorphisms relating hypercohomology groups and the usual chief cohomology group. So the first remark is that whenever we have a chief over a topological space, we can see it as a complex by consider the complex where all the rest of the sheaves in the complex are zero. So the only non-zero element of the complex is F. Once we do this, we can compute the hypercohomology of F, and the hypercohomology group will correspond exactly to the usual check cohomology, and this will be the usual chief cohomology also. So let us consider the following definition now. So take F dot and G dot be two complexes of sheaves over X. We will say that these two complexes are quasi-isomorphic if there exists some morphism of complexes such that whenever we look at the induced morphisms in cohomology sheaves, these induced morphisms are all isomorphism of sheaves, where these cohomology sheaves are nothing else than the quotient of the kernel mod the image in this complex of sheaves. So the result is the following. Whenever we have a quasi-isomorphism of complexes of sheaves, then the induced map in hypercohomology are all isomorphisms. And so the hypercohomology groups are invariant under the relation of quasi-isomorphism. The last isomorphism we will use about hypercohomology groups is the following. So in the case where the complex F dot is an acyclic complex, this means that every term of the complex is acyclic, then we have a simple way to compute the hypercohomology, just as the usual cohomology of global sections of the complex. So note that if we combine the first remark with the last theorem, we will see that in the case where we have only one chief F, and we take F dot to be an acyclic resolution of F, we will have that the hypercohomology of F, which is the usual chief cohomology of F, is isomorphic to the hypercohomology of F dot. This is due to the previous theorem because F and F dot will be quasi-isomorphic. This is exactly the fact that F dot is a resolution of F. And so since this resolution is acyclic, we will get that the chief cohomology of F will be isomorphic to the hypercohomology of F dot, which in turn will be isomorphic to the cohomology of global sections of F dot.
In this video, I am going to explain algebraic de Rham cohomology in a checklist fashion. So, algebraic de Rham cohomology. So this will be basically from chapters 3 and 5 of my book. So we start with the projective variety. We assume that it is a smooth. It's projective variety of dimension equal to n. It's over a field K and characteristic K equal to 0. So what we want to define is this notation, the Rham xk, which we call it algebraic de Rham cohomology. For this one defines something called hypercohomology that I will explain it in our example. And it is the hypercohomology of the complex of differential forms, algebraic differential forms over X. So as said, we have that this complex of differential form, differential operator here, it goes until omega n. When you reach omega n plus 1, it is already 0 because there is no n plus 1, n plus 2 differential form, algebraic differential form over X. And for this, it also will take a covering U with Ui, I in I, with Zariski open sets. And it will turn out that at the end, all these intersection UI0, UI1, UIGs are affine. And so Zariski open set, Zariski actually affine varieties. Anyway, so what I will need to define this SIG. What is this SIG? This is the subset of the product over all ordered set of G plus 1 element, let's say UI0, UIG plus 1 of the covering U. So this will be differential I forms in this intersection of G plus 1 affine variety. And this subset is characterized by skew symmetry property. What is this? This means that omega of permutation of, let's say, I0, Ij. So this permutation will not affect this intersection. So this will be -1 sine of the permutation, the same omega I0, omega I1, omega Ij. And by the way, I have to say that I have taken element omega I0, I1 until Ij. The element of this guy will be denoted by this one. So this product means that I have a bunch of these elements. It turns out if we have a double complex of Sij, so there will be a map from Sij from left to right, Si plus 1 j. This is differential form, and there is also this check cohomology differential operator map, Sij plus 1. So this delta is the differential map in check cohomology. It goes from Sij to Sij plus 1, and its definition is this one. So it is in the intersection of G plus 2 open set. It is just defined as k equal to 0 from 0 to G plus 1. We just make this sum -1 over k fi0, then fik, we just remove fik, and then fij plus 1. And this is the definition of the delta. And here I have to mention that at the end there is a restriction of this guy to this G plus, the intersection of G plus 2 open sets. Anyway, we get this double complex, and when we have a double complex, we get a usual complex in this set. So L0 will be just this one. L1, if this will be sum of these two guys, this one and this one. L2, the sum of these three guys. And in general, Lm upper script, Lm will be sum of Si, Si, j, L plus j equal to m. And we have a differential operator, d, going from Lm to Lm plus 1. And the d on Sig is given by delta plus -1 to the g d. And so this g is the index of the corresponding to check cohomology. And it turns out that this have d composition with d is equal to 0. As once we have this situation, we can define the corresponding cohomology. So we define this cohomology, which is kernel of Lm going to Lm plus 1, this d over the image of map, the same map d from Lm minus 1 to Lm. This fulfill will be the hypercohomology of X of the complex of differential form over K, and the hypercohomology is a more general concept, and in our context, this is just the algebraic de Rham cohomology that we are talking about. Okay, so now we want to discuss the fact that this algebraic de Rham cohomology is the same as usual cohomology when we are working over complex number. And before this one, we have to verify that this consists is independent of the covering U. In the book, you can find all the details of this fact, but for our purpose, we can just ignore this dependency on U. Okay, so whenever you are our complex numbers, we have the C-infinity manifold. Sometimes we put it upper script infinity, saying that this is also C-infinity manifold. And if we look in this way, the complex of algebraic differential forms is inside the complex of C-infinite differential forms. In this way, this inclusion will give me a map from the algebraic de Rham cohomology to the hypercohomology of the same x, sometimes I do not write this upper script infinity, of the complex of C-infinity forms. And this hypercohomology, it is actually isomorphic to the classical de Rham cohomology. So the classical de Rham cohomology, I will just use HM de Rham X algebraic with /RC. So this isomorphism in the book, it is proposition 3.2, but I don't want to make this this separately. Actually, what I want to explain that since we are going to, this is also an isomorphism, so we have this canonical map from A to here, and its inverse from algebraic de Rham cohomology to visual cohomology. And I would like to make the description of these two maps. First, I would like to describe the map R-1 from the algebraic de Rham cohomology to usual de Rham cohomology. So I will take a representative of an element here. So what is this representative? It's a collection of 0 forms, 1 form, and so on. Remember the structure of my double complex, so I am writing similar to the double complex case. So this is my differential form. So its d is equal to 0. And in particular, the delta here is 0. So delta of omega 0 is 0. But something that we'll learn in topology, that the sheaf of differential, C-infinity differential form over x, it is 0 for all m bigger than or equal to 1 and k equal to 0. So these sheaves, C-infinity forms, they do not have non-trivial check cohomology. So once delta is equal to 0, then this means that there will be some eta 0 C-infinity form such that by delta it maps to omega 0. Now the trick is this one. Replace omega with omega minus d eta 0. In the forthcoming discussions, I will ignore some sign problem. It might be minus or plus. One has to write down explicitly. But when you do this one, I will have still the same representative in hypercohomology, but omega 0 will turn out to be 0. So this means that I can assume that omega 0 is 0. And in the same way, we will apply omega, in the next step, omega 1 will go to 0. Again, it will come from some another eta 1. I will modify my element of hypercohomology with differential of this eta 1. I can assume that omega 1 equal to 0. And at the end of the day, after repeating this procedure many times and using that these cohomologies are 0, I can assume that omega is just omega m. This means that there are no other pieces. And so we have the omega m equal to 0. Omega m is alone, so its delta goes to 0, its d goes to 0. This means that delta omega m is 0 and d omega m equal to 0. So what it means, delta omega m equal to 0, this means that the pieces omega m is actually a collection of m forms defined over ui. So this collection of m forms, they glue to each other, they give a global differential form, and this global differential form is closed. And so we will, at the end, we will get an element in the classical de Rham cohomology. Now I want to make the description of the map A from classical de Rham cohomology to algebraic de Rham cohomology. So we have to take a global closed M form, and we have to the get element here. In my discussion, whenever I put check on some notation, this means that's infinity. When I don't put check on some notation like omega, eta, this means that these are algebraic. Hopefully, this will make the understanding smoother. Okay, so let's go. We have this Lm, okay? And so first consider Lm corresponding to C infinity, the complex of C infinity differential form. I start from my omega check. So I will get an element in Lm. How? Omega m check, and omega m check, what it is just the collection of omega check restricted to ui and I, the index of my covering. So this will be its d is equal to 0 because my omega check is exact, and its delta is equal to 0 because this omega m comes from a global differential form. So at the end of the day, this is an authentic element. In this we have d omega m check equal to 0. So from this one, we want to get some algebraic differential form here. So let's assume that we have find a representative, let's say omega m minus 1 until omega k plus 1, it is algebraic, but in omega k it stops. It's not algebraic. That's why I have put 0 here, and the rest are 0. So the idea is that I want to make this omega k algebraic by adding something C infinity here and so on. So let's start. So we know that this d and delta, d of this one is delta of this one up to sine. So what it means, delta of omega plus 1 is equal up to sine, it is d omega check k. What this means? This means that this element is exact, but this element is algebraic. And in one of the lectures, we will learn about a theorem called Atiyah-Hodge. And one part of the theorem says that if an algebraic differential form is exact in C infinity context, it is also exact in the algebraic context. What this means that I can find algebraic form omega k such that at the end of the day, omega k goes with the differential to the same object here. And this means that if I make the difference of omega k with omega k check, it must go by differential to 0. Now, once again, we use Atiyah-Hodge theorem. We have exact differential form. We have, closed differential form. on an affine set. So here, the affine set, the intersection is the intersection of m minus k plus 1 open set. This is a closed differential form. And again, Atiyah-Hodge theorem, the second part, says that this differential form is represented by an algebraic differential form. So so this means that there will be another algebraic differential omega till k, such that this and this, they represent the same element in the RAM cohomology of the affine set. So we just make this replace omega k with the omega k minus omega till k, and we can assume that this guy is, at the end of the day, it is 0. This means that it comes from the by d come from some omega k minus 1. So we are almost done. So we twice used the Atiyah-Hodge theorem, actually two different parts of the Atiyah-Hodge theorem to get this picture. So now we modify omega with the minus. This means that I will add plus minus 1 of this guy to my element. So I had omega equal to omega m plus omega k plus 1 plus omega k check. So once I so here there is a k. Once I do this one, this will be cancelled. Here I will get purely algebraic element, but of course I am doing delta on the other side, so this will turn out to be omega m plus omega baba omega k plus 1 plus omega k. This algebraic, but there will be some non-algebraic thing here coming here, which will be exactly this delta eta k minus 1. So the basic idea is that we can continue this process, and this process reaches until the end, and there we can get a purely algebraic element here, and so we construct the map A. So why we need this map explicitly? The reason is that we have a lot of topological constructions like wedge product in the classical de Rham cohomology, and also the concept of integration, delta being in HM XZ. And since this map A is unique, then we can translate these things here. So here, the wedge product will turn out to be a cup product. And what it means that we can also define the concept of integration with elements here, but what it will be just integration of I minus 1 omega over delta. So the moral of the story is that we can integrate the elements of the algebraic de Rham cohomology over topological cycles.